Today, we're going to be learning about what is actually like a plurality of people's favorite lessons. Like, if you were to ask everybody at the end of calculus, this is like the thing that a lot of people like the very most out of everything we do all year. So I hope you're excited. What we're doing is we're going to use something called L'Hopital's rule to evaluate limits. So before we get into limits, let's see what you guys remember from previous units on limits. Go ahead and do these limits like we already know how to do. And hopefully you were able to remember it. The very first thing we should do is try direct substitution. And when we do, I plug in and I get 1 minus 6 plus 5, that's 0. And I plug in here and I get 1 plus 3 minus 4, which is 0. And when we get 0 divided by 0, it's an indeterminate form. And so we need another limit property to do it. But we should always start with direct substitution. So now this looks like a factor and cancel one. So I'm going to go ahead and factor it. Oh, wait, how are we going to factor this? Okay, what multiplies to make 5? So x plus 5 times x plus 1 multiplies to make 5, adds to be 6. Here we're going to multiply to make negative 4 and add to be negative 3. So negative 4 and positive 1. And we can cancel here. The x plus 1 will cancel out. And a nice trick when you're factoring and canceling is whatever this goes to, there's got to be a factor of that on the top and the bottom if they both went to 0. Because like if they go to 0, then negative 1 plus 1 is going to make it 0 on both. So it had to have that factor. Okay, so we're doing the limit as x goes to negative 1 of x plus 5 over x minus 4. And now we can just do direct substitution because it doesn't come out to be 0 over 0. Negative 1 plus 5 divided by negative 1 minus 4. And so that is 4 divided by negative 5, which we never leave a negative in the denominator. So this is negative 4/5. So there is our first limit. Our second limit, hopefully you remember how to do it, but if not, this one was a little weird. Here we can use our limit property to bring the constant outside. So 5 times the limit as x goes to 0 of sine of x over x. And this was one of our special limits. We should recognize that the limit as x goes to 0 of sine of x over x is just 1. That was one of our special trig limits. I guess before we did this, we probably should have checked to see if it was indeterminate. And when we plug in 0, we do get 0 over 0. And so that's an indeterminate form. But this limit goes to 1. That's a special limit we should have memorized. And so this limit is 5. The last one, if you were to start by factoring and canceling, you'd be in deep trouble. You really hopefully started by plugging directly in, because this time when we plug directly in, it does not go to 0. This is 3, I believe. And when we plug in the denominator, we get 4 minus 3, which is 1. And so direct substitution tells us that this limit is 3. So that's nice. This one was the easiest one. Now we're going to do something weird. And this is what L'Hopital's rule involves. It involves using derivatives to help us find limits. So instead of doing the limit of the top over the bottom, what I want you to do instead is do the limit going to the same place. So if it was the limit as x goes to negative 1, it's still going to be the limit as x goes to negative 1. But now do the limit of the derivative divided by the derivative. And so for this first one, it's the limit as x goes to negative 1 of the derivative of the top divided by the derivative of the bottom. This is not the quotient rule. We're not doing any sort of quotient rule thing here. We're just doing the derivative of the top and the derivative of the bottom. So hopefully you got that this is 2x plus 6 and 2x minus 3. And now we can do direct substitution. 2 times negative 1 is negative 2, and negative 2 plus 6 is 4. 2 times negative 1 is negative 2. Negative 2 minus 3 is negative 5. And we get negative 4/5. That's that limit of the derivative divided by the derivative. Okay. How about for b? This was a. How about for b? What limit should we do here to do the limit of the derivative over the limit of the derivative? We're going to be doing the limit. It's going to be the same thing. It's still going to 0. Limit as x goes to 0. Of the derivative of the top, the derivative of a constant multiplier is going to stay. The constant multiplier is going to stay. The derivative of sine is cosine. And the derivative of x is just 1. And now we can do direct substitution. Cosine of 0 is 1, and 5 times 1 is 5. So 5 divided by 1 is 5. Great. Cool, cool, cool. Hopefully we are noticing something so far. This might be a minute to pause and notice and predict how this next one's going to go. This next one, we're going to do the limit as x goes to 4 of the derivative of the top. The derivative of 15 is 0, it's a constant, divided by the derivative of the bottom. The derivative of x minus 3 is just 1. And this time, 2 times 4 is 8, and 8 minus 7 is 1. 1 divided by 1 is 1. So what did you notice about these three limits? And I hope we noticed that these two are the same, and these two are the same, but these ones are not the same. And so there's this kind of like weird trick where, hey, you can do the derivative of the top and the derivative of the bottom, and sometimes that makes it much easier. Like this one was, I bet a lot of you forgot how to do this one from the first semester, but doing it this way is quite easy. But sometimes it doesn't work. And so the question is, what was different about this third one that you might think made it not work? Pause the video for just a second and think, what made this one not work? And hopefully you noticed that the difference here was that these two were both indeterminate forms, but this one we could do with direct substitution. And so we were able to do it as the derivative over the derivative when it was indeterminate. And that's what L'Hopital's rule tells us. Let's look at this right now. L'Hopital's rule has a couple of conditions, and this is important on the free response portion of the AP exam. If you have two continuous functions at the place where you're doing the limit, and the limit of the top and the limit of the bottom are both equal to 0, because that would be an indeterminate, or both equal to infinity, that's another indeterminate, then you'll get an indeterminate form. And when you have that kind of indeterminate form, you can, instead of doing the limit of the top over the bottom, it will be equal to the limit of the derivative of the top divided by the derivative of the bottom. You can just do the derivative of both of them, and this will, a huge amount of the time, make this much easier. In fact, guys, when I'm like grading your quizzes at the beginning of the year, I am entirely doing this. When you're doing all these like limit tricks, I am just doing L'Hopital's rule. And a lot of kids ask, like, you're going to see in a second, like, how much easier this is. They say, like, well, why didn't you teach us this at the beginning of the year? Well, if you recall, we learned about limits and used limits to come up with derivatives. How could we have used derivatives to do limits when we used limits to come up with derivatives? Derivatives came afterwards. But once you learn about derivatives, one of the cool applications you can do is go back and do limits more easily because they are connected. In fact, I just want to show you something. The limit definition of the derivative, the limit as h goes to 0 of f of x plus h minus f of x over h. This is an indeterminate form. When you plug in h is 0, you get f of x minus f of x, which is 0, over 0. That's indeterminate. And this limit definition of the derivative is literally just f prime of x, which is the derivative of the top with respect to h. So like if h is the variable, then this is a constant. And so it's just f prime of x is what the derivative of this one is. So it's f prime of x plus h times whatever, h prime. And then when we do plug in h equals 0, you'll just get f prime of x. So the chain rule works out there. Okay, so let's see how this works. As x goes to 1, this is actually like a limit I don't know how to do without L'Hopital's rule. And so what we want to do is we want to start by checking, can we use L'Hopital's rule? Checking to see if you can use L'Hopital's rule involves seeing if a function is continuous. And log functions and polynomial functions are both continuous, so you're able to use that. And the second thing is they both either need to both be 0 or both need to be infinity, but you're always going to start with direct substitution anyway. And if direct substitution works, you're done. And if it doesn't work, then you do L'Hopital's rule. So natural log of 1, so e to what power gives you 1? Well, that's 0. So we get 4 times 0, which is 0. And 1 minus 1 is 0. And so we can use L'Hopital's rule here. This is the limit as x goes to 1 of the derivative of the top, which is 4 times the derivative of natural log of x is 1 over x, divided by the derivative of the bottom, which is just 1. The derivative of x is 1. The derivative of minus 1 is 0. And now we can just plug in 1. We use direct substitution. 1 divided by 1 is 1. 4 times 1 is 4. 4 divided by 1 is 4. And so it's a very quick and easy way, and this would have been impossible to do without L'Hopital's rule. Try this next one on your own. What are the two conditions that need to happen? Well, they are met because the top one is an exponential minus an exponential, and exponentials are always continuous. Subtracting two continuous functions is continuous. And the bottom one is linear, which is also continuous. So they are continuous functions. And the other thing is we need to do direct substitution. E to the 0 power is 1. E to the negative 0 power is the same as e to the 0 power, which is 1. And as x goes to 0, we get 0. This is 0 over 0. And we actually don't want to write equals because this would be saying this limit is equal to undefined. We just want to like show it off to the side. So 0 over 0 is an indeterminate limit. And we can use L'Hopital's rule. So go ahead and do that. It is, L'Hopital's rule says we will keep the limit the same, but we're going to do the derivative of the top. The derivative of e to the x is e to the x. The derivative of e to the negative x that is a chain rule. So it's going to be e to the negative x still times the derivative of negative x, which is negative 1. So negative 1 times negative e to the x is a positive, divided by the derivative of the bottom. So we had to do the chain rule here. Remember, the derivative of e to the x is e to the negative x times negative 1 because of the derivative of the inside function. So we had to use the chain rule there. Now we can just do direct substitution. E to the 0 is 1. E to the 0 is 1. And 1 plus 1 is 2. 2 divided by 1 is 2. Okay. How about this next one? Limit as x goes to infinity. And I actually find it really helpful to do this one graphically. Like the natural log of x looks like this. As you go towards infinity, the natural log of x is going towards infinity. Okay. How about x? Well, as you put in bigger and bigger numbers, the numbers get bigger and bigger. This one's also going to infinity, so we get infinity over infinity. And, you know, as x goes towards infinity, natural log is continuous and x is continuous. They're both going up. So go ahead and do L'Hopital's rule here. So it's going to be the limit as x goes to infinity still of the derivative of the top divided by the derivative of the bottom, which is 1. And now I can plug in infinity. 1, as x goes towards infinity, 1 divided by infinity is going towards 0 because you're dividing by a bigger and bigger number. We learned that in Algebra 2, and I hope you did it in pre-calculus, that as you're putting in a bigger and bigger number, this one's going towards 0, and then 1 is still staying at 1, so we go towards 0. So this limit is 0. Okay. This next one, I see this doesn't quite look the same. And in fact, you cannot use L'Hopital's rule on just any limit. If you have it's only when you have f of x over g of x where it's an indeterminate form. Is this f of x over g of x? Well, kind of, but there's this extra multiplying part. So this is not f of x over g of x right now, but we can really easily rewrite it into a form that we could do L'Hopital's rule on. So this is a technique we will often use when there are things multiplying. We want to think like, hey, could we rewrite this? So we just put this over 1, and 8x will multiply times 1. So this is the limit as x goes to 0 of 8x times 1 is 8x, 3x times 1 is 3x. And now we can do it. 8x is continuous, 3x is continuous. As x goes to 0, we'll get 0 over 0, which is indeterminate. And so we can do L'Hopital's rule here. So it's the derivative of the top, which is 8, divided by the derivative of the bottom, which is 3. And the derivative of a constant, as x goes towards 0, 8/3 is just going towards 8/3. Remember that the limit of a constant is that constant. You know, you also could have done this with factor and cancel, because it's 8 times x divided by 3 times x. Well, you can just cancel out an x and get 8/3 that way too. So that's another way you could have done it. All right, why don't you guys look at this one? This is not set up to be a L'Hopital's rule. How can we change it to L'Hopital's rule? Well, hopefully we recognize that this is the same as 4x times e to the negative x. Negative exponents are dividing. This is 1 over e to the x. And now we can see what's going on here. We can do limit as x goes to 0 of 4x over e to the x. And we need to check our conditions. 4 times 0 is 0. E to the 0 is not 0. E to the 0 is 1. And this one is not L'Hopital's rule. This is direct substitution. 0 over 1 is 0. We don't use L'Hopital's rule here. And look what would have happened if you had tried. If you had said this is the limit as x goes to 0 of 4 over e to the x, this would have looked like it was 4 over 1, which would be 4, and this would be wrong. So remember, you do need to check to see if direct substitution works. And the good news is, if direct substitution works, you're just done, right? So like this one up here in our warm-up, you should try direct substitution first. If it works, great, you're done. And if it doesn't work, then you do L'Hopital's rule. You don't need to do L'Hopital's rule if it worked, you're already done. Here's another slightly different one. This is not L'Hopital's rule right now because it is subtracting. But let's go ahead and try to evaluate it. This is limit as x goes to pi over 2. I don't know what secant of pi over 2 is, so I always change it to sines and cosines. We should know that secant is 1 over cosine of x minus sine of x, tangent is sine of x over cosine of x. And now it's starting to actually look a little bit more like a L'Hopital's rule situation, isn't it? Because we've got fractions. Cosine of pi over 2 is cosine of pi over 2 is 0, so we get 1 over 0. Cosine of pi over 2 is 0, so we get 1 over 0 again, and this is an indeterminate form. You've got something that's not defined minus something that's not defined. This is an indeterminate form, and so we want to see, can we get it just like we had over here? By the way, this indeterminate form was 1 over 0 times 0. This is another indeterminate. There's like all these indeterminate forms where you're like, I don't know what number that is because there's something undefined there. So can we get this into a L'Hopital's rule situation? And the answer is yes. They have a common denominator, and so we can combine them. This is the limit as x goes to pi over 2 of 1 minus sine of x over cosine of x. And just as we saw before, this is 0. Sine of pi over 2 is 1. And so 1 minus 1 is 0, and we get 0 over 0. They are both continuous. Trig functions are always continuous. And so we get, to use L'Hopital's rule, of the derivative of the top, the derivative of sine is cosine. The derivative of 1 is 0. And the derivative of cosine is negative sine. And so now, when I plug in pi over 2, cosine of pi over 2 is 0. Sine of pi over 2 is 1. And this is direct substitution now. So it's 0. Okay? So hopefully you're feeling okay about that. You get a lot of chance to practice L'Hopital's rule ones. Let's see how this can come up. So where does this function have a horizontal asymptote? So is this a L'Hopital's rule question? The answer is yes. And we learned how to do this in Algebra 2, but we're going to learn how to do it in calculus real quick. Remember that horizontal asymptotes are what's happening as x goes towards infinity. And you should have learned in pre-calculus that you can actually have 2 different horizontal asymptotes on each side. And so you do need to check both as x goes towards infinity and as x goes towards negative infinity. So finding the horizontal asymptote is the same as doing the limit as x goes to infinity and the limit as x goes towards negative infinity. So as x keeps going to the right, what's y getting closer to? And as x keeps going to the left, what's y getting closer to? And so let's do that. So the limit as x goes to infinity of 5x squared minus 3x plus 1 will get the horizontal asymptote. Why did I put that minus 5? We'll get the horizontal asymptote that's on the right side, if there is one. And when I plug in infinity, infinity squared is infinity. And so this whole top thing is infinity. Infinity squared, we get infinity over infinity. Okay, so this is an indeterminate form. We can use L'Hopital's rule. So this is the same as the limit as x goes to infinity of the derivative of the top divided by the derivative of the bottom. And as I go towards infinity, they're both going to infinity again. And so this is still infinity over infinity. And guess what? We did L'Hopital's rule, but it's still going to infinity over infinity. We're allowed to use L'Hopital's rule again because we're just doing a limit. L'Hopital's rule is just like, well, what do you do if you're doing a limit? Well, we're doing a limit. So we can do the limit as x goes to infinity of the derivative of the top divided by the derivative of the bottom. And now this is direct substitution. This is 5/3. There's no infinities left. There's no x's. This is just a constant. As x goes towards infinity, 10/6 is just 5/3. We can simplify it. So notice sometimes you have to do the L'Hopital's rule twice. Okay? Sometimes you have to do it more than twice. But you can see how the powers are going down. This should remind you, in Algebra 2, we learned that if the degree on the top is bigger than the degree on the bottom, it'll go towards infinity. If the degree on the bottom is bigger than the degree on the top, it'll go towards 0. And if they're the same, it'll actually end up being these coefficients divided by each other. But you can do L'Hopital's rule if you forget that. Now, we really should do the limit as x goes towards negative infinity here. As x goes towards negative infinity squared is going to be positive infinity. So we'll end up getting positive infinity over positive infinity. And so as we do L'Hopital's rule, we'll get the exact same thing, except we'll get it with negative infinity in here. But it's still a constant, right? So it doesn't really matter if it's negative infinity. You still get 5/3. So in this case, the asymptote is the same both to the left and to the right. And that's actually how it was always in Algebra 2, but in pre-calculus, I hope we learned that sometimes the limits are not the same on both sides. So we do need to check as x goes both towards infinity and negative infinity. So that's nice. All right, how about here? Do this one on your own. Try this one on your own. Do this limit. Hopefully you started by doing direct substitution. I always draw a unit circle if I'm not sure. Cosine of 0 is 1. 1 minus 1 is 0. E to the 0 is 1. 1 minus 1 is not 0. So this one is, man, you know what's funny is I think I meant to make this work out, but if you do this, if you check it like you should check it, oh, sorry, this is right. Oh man, I was like, this didn't come out to be 0 over 0. So the top is 0. We found that. E to the 0 is 1. X is going towards 0, so it's 1 minus 0 minus 1, which is 0. So 0 over 0. It is an indeterminate form. These are both continuous functions, and so we can do L'Hopital's rule. So the limit as x goes to 0 of the derivative cosine of x is negative sine of x. The derivative of e to the x is e to the x. The derivative of x is 1. And as x goes to 0, we get 0. Sine of 0 is 0. It's the y value. Over e to the 0 is 1. And 1 minus 1 is 0. And so we can do L'Hopital's rule a second time because it's still 0 over 0. The derivative of sine of x is cosine of x. The derivative of e to the x is e to the x. And as x goes towards 0, cosine of 0 is 1. E to the 0 is 1. And our answer is negative 1. Yeah, so we can do that. Sometimes we have to do L'Hopital's rule twice, and that's okay. All right. F of 4 is 3, g of 4 is 2, f prime of 4 is 6, g prime of 4 is negative 3. Evaluate these limits. Now, the first thing we're going to do is direct substitution, but we also need to check and see, are these functions continuous? Because it didn't tell us the top was continuous, but what it does tell us is that at x equals 4, f prime of 4 exists. And if a function is, so let's pretend this is on the free response where you're not just like finding the limit. This is the first one where it hasn't been clear that the function is continuous on the top and the bottom. So we need to kind of prove that the top is continuous, and it didn't tell us what f of x is. So how do we know it's continuous? Always before we were like, oh yeah, this is a continuous function, this is a continuous function, no problem. But here, it didn't tell us that f of x is continuous, and we only need that f of x is continuous at x equals 4. But because f is differentiable, at x equals 4, right? If a function is differentiable, it's automatically continuous. And if you subtract two continuous functions, it's still continuous. So f of x minus 3 is continuous. And because g is differentiable at x equals 4. These quotes say the same thing that was above. Because g is differentiable at x equals 4, then when we multiply g of x times something that's continuous, it'll still be continuous. And when we subtract a continuous function, it's got to be still continuous. So the fact that they told us the derivative means that because it's differentiable, because the derivative exists, we learned last semester that that means the function must be continuous. So we actually need to state this. We need to say, hey, here's how we knew the numerator was continuous and how we knew the denominator was continuous. It's because they told us what the derivative was there. So it's differentiable, and so it's continuous. And I guess if we're in free response mode, let's go ahead and plug it in. So the limit as x goes to 4 of f of x minus 3 is equal to f of 4 is 3. So 3 minus 3 is 0. And hopefully that's the same as the limit as x goes to 4 of x g of x minus 2x. Let's see, this is 4 times g of 4 was 2 minus 2 times as x goes to 4. This will be 4. 8 minus 8 is 0. And so yes, these are equal to 0. So we can do L'Hopital's rule, but we had to work at it a little bit there to actually prove that the numerator and denominator were both continuous. We had to use the fact that they told us they were differentiable by telling us the value of the derivative. Therefore, they were continuous. And you actually have to say it. There was a year that the AP graders were really angry. It was actually my first year grading nationally, and a lot of the people were like really upset because in the problem it said like f of x is differentiable, and they required for the students to get the point. The people who wrote the test that year required for the students to get the point that they needed to say, because f of x is differentiable, f of x is continuous, and so you could do L'Hopital's rule, right? Like everybody said this part. They said like, okay, the limit of the top is 0, the limit of the bottom is 0. So they wrote that part, but a lot of kids assumed that because it said it was differentiable, they didn't need to write it was continuous. And on the AP exam, you needed to have written that year to get this point. So because we can do L'Hopital's rule, L'Hopital's rule says we do the limit of the derivative of the top. The derivative of f of x is f prime of x, and the 3 will go to 0, divided by the derivative of the bottom. And the derivative of the bottom, this is a product rule, so it'll be the derivative of the first one times the second left alone, plus we're going to leave the first one alone times the derivative of the second. So that's the derivative of this guy, minus 2, because the derivative of 2x is 2. And as x goes to 4, let's see, f prime of 4 is 6. G of 4 is, I wrote too many things here. G of 4 is 2. X is going towards 4, so I'm going to plug in 4 with direct substitution there. 4 times G prime of 4 is negative 3. And we've got minus 2 here. So 6 over 2 minus 2 is 0. This is negative 12, and we get negative 1/2. Okay. I'd just like to point out a few other things. While we're talking about free responses, you have to write this. Like, you have to write the limit again. Like, sometimes kids will just write like equals f prime of x over this, and that is not true. You need to actually write the limit again, because that's what L'Hopital's rule says. L'Hopital's rule says the limit of something is equal to the limit of the derivatives. If you don't write the limit both times, then you haven't written the same thing, and it's not correct. All right. f and g are differentiable. So since f is differentiable, this will be continuous. Since g is differentiable, this will be continuous. Continuous, 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 continuous. If they tell you it's differentiable, like kind of everything involved with it will be continuous. But if you are on the free response portion of the AP exam, you would need to write, hey, f of x minus 4 is continuous, 6 minus 2 g of x is continuous, and, let's actually do direct substitution here. The limit as x goes to 1. Go ahead and do this on your own. I don't know what it'll come out to be yet. I haven't done this in a year or two. Let's see. So hopefully you got it, but if not, as x goes to 1, f of 1 is 4. And so we get 4 minus 4. As g goes to 1, g of 1, when x is 1, g of x is 3. So we get 6 minus 2 times 3. So this is 0 over 0. So the derivative of the top and the derivative of the bottom are both going to 0. And so we can do the limit. Make sure you're writing the limit of the derivative of the top divided by the derivative of the bottom, which is negative 2g prime of x. There's no product rule or anything here. These are just constants. This constant goes to 0, and this is a constant multiplier. So f prime of 1 is 5, and g prime of 1 is 1/2. So negative 2 times 1/2 is negative 1. So we get negative 5. All right, this next one, let's see how you guys do on it. I can see immediately that the bottom is going to 0, but let's look at the top. F of 3 is 7. G of 3 is negative 4. And so we get 0 over 0. And so we can do L'Hopital's rule here. So limit as x goes to 3 of the derivative of the top. This one's a constant, goes to 0, divided by the derivative of the bottom, which is just 2. And as x goes to 3, f prime of 3 is 3/2 plus negative 1 is what g prime of negative 3 is, over 2. I can simplify this if I want. This is 3/2 minus 2/2, and that's 1/2. Dividing by 2 is the same as multiplying by 1/2. This is 1/4. If you're on the free response portion, you could leave your answer here, and this would get you full credit. Remember, you don't have to simplify on the free response, so you could leave it like this. Okay, as x goes to 1, let's check this. F of 1 is 4, so 4 plus 2. This is not going to 0 over 0, I can already tell. G of 1 is 3, and so we get 6 over 1, which is 6 by direct substitution. And if you try to do L'Hopital's rule here, you'll get it wrong. It will not come out right. So always see if you can apply L'Hopital's rule before you just do it. There's a reason the AP exam makes you show that you know when you can do L'Hopital's rule, is because, if you just start doing L'Hopital's rule on everything, it doesn't work out. Ooh, this is really good. Oh, I was good when I wrote this. This is a very nice problem. Okay. So it says a and b are integers, and this limit is equal to b. What is a plus b? Well, let's start by doing the limit using direct substitution. So the limit as x goes to 1 is 2 times f of 1 is 4. So 2 times 4 minus a. G of 1 is going to be 3. And so we get 8 minus a over 0. Now, how are we supposed to get that this is equal to b? Well, the first thing you should notice here is that in order for this limit to exist, if the denominator is 0, remember from earlier in the year that if the numerator is not 0, that limit goes towards infinity, and the limit doesn't exist. But b is an integer, so the limit must exist. If the denominator is 0, the only way for the limit to exist is if the numerator is also 0. And so that tells us what a has to be. 8 minus a has to equal 0, And so a has to equal 8. That way we get 0 over 0, which is an indeterminate form. If the denominator is 0 and a was anything but 8, we would get like 7 over 0, which would be undefined. And so it wouldn't equal b, which is an integer. So it told us that this limit was equal to b. And since the denominator goes to 0, the numerator must also go to 0. So a is 8. So let's go back up here and say that if a is 8, then I can do the derivative of this. So a is 8. And now we get 0 over 0, and so I can do L'Hopital's rule. So it's the limit as x goes to 1 of the derivative of the top is 2f prime of x. The derivative of the bottom is g prime of x. F prime of 1 is 5, so 2 times 5 is 10, divided by 1/2. 10 divided by 1/2 is the same as 10 times 2, multiplied by the reciprocal, and so we get 20. So this limit is equal to 20, and that's what b is. So b is 20, and a is 8, and the question asked us what is a plus b, so a plus b is 28. Wow, cool problem. So you had to realize that in order for this limit to exist, a had to be 8, and then you could use L'Hopital's rule because it's 0 over 0, and get it that way. Okay, here's a graph. Limit as x goes to 1 of f of x minus 2 over g of x. F of x and g of x are both continuous, so we are able to do L'Hopital's rule if it's 0 over 0. Let's actually plug in. F of 1 is 2, so we get 2 minus 2. G of 1 is 3, and so we get 3 minus 3, and we've got 0 over 0, and so we can do L'Hopital's rule. It'll be the limit as x goes to 1 of the derivative of the top divided by the derivative of the bottom. And so f prime of 1, we don't have an equation, but remember that f prime of 1 is the slope of the tangent line, and this is just a linear function, so we can see what the rise over the run is. It goes up by 2 and over by 1, up by 2 and over by 1. The derivative, the slope, at x equals 1 of f of x is 2. The g prime of 1, when we plug in with direct substitution, g prime of 1 is the slope of g of x at x equals 1, and g is going down by 3 and over by 1. So 2 divided by negative 3 is negative 2/3. Okay, let's see over here. Okay, when we plug in with direct substitution, we get f of 6. So, okay, 1, 2, 3, 4, 5, 6. And which one is f? Okay, f of 6 is 1, 2, 3. Okay, so we get 3 minus 3. G of 5 is going to be 2. We get 2 minus 2. So we get 0 over 0 there. Great. We can do L'Hopital's rule. So it's the limit as x goes to 1 of the derivative of the top. Here, this is chain rule. It's the derivative, f prime with 6x left alone inside of it, times the derivative of the inside, which is 6. Same thing on the bottom. G prime of 5x times the derivative of the inside, which was 5. Let's see if we can do direct substitution now. The slope at x equals 6 of f of x is, what is the slope here? It's going down by 1 and over by 1, 2, 3, 4. So we get negative 1/4 times 6 divided by the slope of g at 5. The slope here is, it's going up by 2 and over by 1, 2, 3. So 2/3 times 5. Yuck, this is an ugly fraction. So we get negative 6/4 divided by positive 10/3. And when we divide fractions, we multiply by the reciprocal. So multiply by 3/10. I can simplify a little bit here before I multiply. I can divide by 2 and divide by 2. So 3/2 divided by 3/10. I could have simplified at any point there, but this is simplified here. So when we multiply across, we get negative 9/20. All right. Hopefully you're feeling pretty good about L'Hopital's rule. I think it is really useful. You guys should go check out like your quiz from the first unit or something and see how easy it makes what was a fairly difficult quiz at the beginning of the year. Once you know that you can just do, you always have to try direct substitution first. We talked about that a lot at the beginning of the year. But if you've tried direct substitution, then you can go ahead and do L'Hopital's rule on it. All right, have a good day. Welcome back to school. Hopefully you're feeling good about your learning, and let me know if you have any questions.